Finding areas in VCE methods may seem really easy at first, but what the examiners and your teachers like to do is make it infinitely more complex than it has to be. And here's an example of one where this has actually been asked on past SACs and past exams, and it's where your area may not be as easy to calculate as it first seems. In this case, we have a log curve, and the shaded area that we're asked to calculate goes from x equals 1 to x equals 3. And at first glance, what a lot of students would do is try and integrate log, but the problem is that the integral of log is actually not in the course, it's not on the formula sheet, and it's something that we actually not expected to memorize. So if you have a tech-free exam where they ask you to find the area of this shaded region here, it would actually be very hard to find and almost impossible by trying to find the integral of log. Obviously, it's a bit different if you have your calculator. You'd probably be able to find a rule or an expression for the integral of log, but in this case, we actually can't. So we have to be creative and think about how else we can find this area here. Now, what we do in this question, I'll just give it away because obviously you're here to look at how to do these types of questions, and hopefully it gives you a bit of exposure to more creative problem-solving techniques, is actually recognizing that we do know a lot of information about this curve, and in particular, if we find the inverse of this curve, we actually know a lot about that function, and the inverse of log e of x we should know is y is equal to e to the power of x. Obviously, if I just swap x and y, I can rearrange and I get y is equal to e to the power of x. So I'm going to draw this on the same graph just to illustrate, what that looks like and how it relates to our original function of y is equal to log e of x. So we should know that inverse functions and the original functions are symmetrical about the line y is equal to x. And more importantly than that, your coordinates actually swap our locations. So for example, if this is y is equal to log e of x and we have an x-intercept at x equals 1, then this function actually has a y-intercept at y is equal to 1. And if we want to reflect this area as well, go further than the coordinates, but also the area as well, we know that the shaded region, it might not be the same shape because I've drawn it kind of badly, but this area should go from y is equal to 1 to y is equal to 3. So this is the same area, so the black area is the same as the blue area, it's just reflected, and we know a lot more information about this curve, namely the integral, more so than the green curve, which is y is equal to log e of x. So this is y is equal to e to the power of x, and that's the area that's equivalent to the blue area. So now it's just a matter of finding this area and making that equal to this. So how do we find the black area? What we know is that when we find the integral of something to find the area, it gives us the curve that's the area that's underneath the curve and bound by the x-axis. So let me just get a new color. If I integrate this, what happens is that this area here will be calculated, and if we integrate from here to here. So what we have to do is just find that red line there. We know that the starting integral is 0, well, x equals 0, so we just have to find that point there. That's kind of easy to find. All we can do is just say 3 is equal to e to the power of x. Therefore, x is equal to log base e of 3. So therefore, this coordinate here has an x value of x is equal to log base e of 3. Now, if I wanted to find the red area, what I do is I just integrate y is equal to e to the power of x from x equals 0 to x is equal to log e of 3. Now again, that kind of gets us one step closer to what we're trying to find, which is the black area. All I have to do once I find the red area is find the area of the big box. Again, I'll use a different color. So I'll find the area of the box here, and I'll minus the area, the red area, and that's going to give us my full area or my remaining area, which is black. Now, just to reiterate, if I want to find the goal area, I have to find that full blue region, which is the rectangle, and then minus that red region. And I know how to calculate both because I have enough information to do so. And I didn't have enough information when I started this question because it was just a log curve, which I don't know the integral of. So what we do is we just calculate these two things and find the difference of them. So the blue curve, that's really easy to calculate. It's just the area of a rectangle. So what we do is the x value is log e of 3, the y value is 3, so therefore this area here is 3 log base e of 3. Now the red area is a bit harder to calculate. It's just the integral though of e to the power of x, and that goes from x equals 0 to x is equal to log e of 3. So 0 log e of 3 dx. So I'll just go ahead and simplify this. So 3 log e of 3 minus the integral of e to the power of x. Very easy, hopefully you don't forget this one. It's just e to the power of x. And that goes from 0 to log e of 3. 3 log e of 3, and then I substitute this in. So I end up getting e to the power of log base e of 3 minus e to the power of 0. Pretty easy, e to the power of 0 is 1. E to the power of log base e of 3, the e's and the logs are kind of opposite, well, they're inverse functions, but they actually cancel each other out algebraically as well. It's the same as x squared to the power of 1/2. We know those things combine and cancel each other out. In this case, exactly the same thing, so we're just left with 3 for this expression here. So therefore, and it's 3 log e of 3 minus this whole bracket here. So it ends up being, when we expand this, it ends up being minus 3 plus 1. So we end up getting 3 log e of 3, bit of a tongue twister, minus 2 units squared. So that's that black area there, that little quadrant there, and that's the same as the blue area here due to our reflection properties with our inverse functions.